Explore the biggest questions of our time and get to know the people behind the science. This is Curiosity Meets Discovery, research talks from inside the Max Planck Society.
I wonder, how many of you have ever been curious about the almost unfathomably complex universe that our Earth is a part of? And how many of you have wondered if it would be possible to understand the fundamental principles that underlie the organization of galaxies and the movement of the planets and stars within them? Okay, most of us don't dare to go there. But our guest today, Dr. Reinhard Genzel, astrophysicist at the Max Planck Institute for Extraterrestrial Physics, has not just thought about this, he has devoted his career to the development and application of new technologies that have made it possible to visualize the stars of our universe with unprecedented resolution. His work resulted in him being awarded the 2020 Nobel Prize in Physics for the discovery of a supermassive compact object at the center of our galaxy, otherwise known as a black hole. Reinhard joins us today to share the scientific odyssey of black holes, from Einstein's prediction to his experimental discoveries that confirmed the existence of black holes. And he will explain how he thinks our understanding of the universe will evolve in the coming years. Thanks for sharing your science with us today, Reinhard. And I look forward to our discussion of this fascinating topic following your presentation.
Well, thank you very much. So the story which I will tell you about is actually a story of research in physics, which has now a time scale of almost 105 years, because it has to do something about gravity. You want to understand this strange thing we know about as human beings, right? We cannot jump very high. The gravity of Earth brings us back down, and gravity dictates the world on the largest scales, remarkably so also actually on the smallest scales, which we haven't yet studied. So it's a very mysterious kind of a thing. And 100 years ago, there was Albert Einstein, and he presented a theory which refined what was known about gravity in many very surprising ways. Of course, Newton already knew, and Kepler knew, that if you have a mass like the sun, for instance, and you have planets in the vicinity of the sun, which are gravitationally bound, well, then they move in what we would call orbits, like circles or ellipses or whatever. But Einstein's theory, expanded this story and basically showed that what really is happening, you could think of as a distortion of the four-dimensional space-time, as he called it. So we know, of course, about the three dimensions of space, and then the fourth dimension is time. So emotion in space-time then would be this little red planet, if you like, move along this dashed cyan curve through space-time, and the mass of this green or yellow ball being much larger than that of the red ball would dent space-time such that the orbit of the red ball would be influenced by the presence of that mass. So that's a way describing what gravity does. Now, this sounds, a bit of a mathematical specialty, and indeed it was. It's a very difficult set of equations, which initially interested mostly the mathematicians. Only later, this became of interest to broader scientists in astrophysics, physics, and cosmology, and so forth. Now, one of the main new things in Einstein's theory, apart from this space-time description, is the fact that in his theory, also light experiences gravity. That was not known and was not in Newton's theory. So that when you have, for instance, a star, which is at some distance away, and you're looking at the sun and the star behind it, then the light is getting bent towards the sun. And so if you look from the Earth, you think that the star is in a different location, further out than it really is. And in fact, this bending of the light is something you can actually observe when there is an eclipse. So when Einstein did his theory, he made a calculation what that would be for a distant star during a solar eclipse, and he basically calculated that this displacement was about 1.5 arc seconds. That's a very small angle, but it's one which in principle can measure. And indeed, in 1919, only 2 years after his theory was published, there was a solar eclipse near the equator, and Eddington and other observers went down there and observed it, and they looked at a number of stars, which were very, very well known during that eclipse, and when, in fact, these stars were behind the sun. And what they found were exactly these 1.5 arc second difference from the position which they would have had if the sun wasn't there. So clearly, this effect of general relativity on photons, as we say, was a reality. And that was a sensation, because nobody would have expected it. And certainly, as I said, it was not predicted in Newton's theory. Now, another year later, Karl Schwarzschild, whose image you see there in the top, found one solution for such spacetimes around the mass in the limit of different masses and different sizes. And so again, if you think of the effect of gravity on photons, then in the theory, the effect on photons can be very, very substantial, and there can be objects where light cannot really escape anymore. Let me explain that to you. Let's think of the sun. So here's a picture of the sun, and of course you could, in your mind, put a rocket on the surface of the sun and let it fly into space. And we know from rockets on Earth, you would have to give that rocket quite some speed at the Earth. That's about 11 kilometers per second. In the case of the sun, it's about 600 kilometers per second in order for the rocket to escape from the sun and go all into outer space. Now that depends on the mass of the sun, of course, but also on the size of the sun. So if you, in your mind, leave the mass of the sun constant, but make the sun smaller. In fact, let's make it as small as 3 kilometers. And then again, we calculate what speed the rocket would have to have in order to escape. And all of a sudden we find that this is 300,000 kilometers per second. Why is that important? Well, 300,000 kilometers per second is the speed of light. So if I make the sun still a centimeter smaller, then the rocket would have to move with more than the speed of light, and that cannot go. There were very clear experiments, the so-called Michelson-Morley experiments in the late 19th century, which showed that speed of communication between any 2 points in vacuum cannot be larger than that of light. So light is, so to speak, the speed limit of communication. And therefore, if there were any emission of light from this mini sun, if you like, then we couldn't see it. And then this object would be a black hole. At least that's what we call it now. And this black hole has one characteristic we now understand, which is a characteristic radius within which any information which is generated there cannot get to us. We call that an event horizon. An event horizon which separates our world and that within this strange object which in general relativity comes out of these equations. Now, the event horizon size is proportional to the mass. So if I increase the mass, then the mass of the size of the event horizon increases. So for instance, for the Earth, the event horizon of the Earth is 1 centimeter. So if I compress the Earth to 1 centimeter, then it would be a black hole. There's a second thing about this, which is a little harder to explain, which is that the theory says that if you turn the rocket around and fly inside into the black hole, assuming that you are a stable rocket and you don't get drawn apart by tidal forces, well, then you would find yourself coming to the center of inevitably to the center of the mass within a finite period of your time, and all other masses too. You cannot stop the rocket anymore, if you like. That's like the Niagara Falls. If you're a boat on the Niagara Falls and you're falling over the edge, there's no way you can decide that you want to go back up. All right, so the mass then in a black hole, in the theory, is all within a zero extent mass singularity. That's a very, very strange and weird prediction. So that's the properties of these black holes in a nutshell. And general relativity, as I said, predicts these and a number of other things already early in the 20th century, and was discussed then, but remained pretty much a mathematical discussion, because where would you find such objects? And actually, how would you see them if they're black? Well, the answer is, think of a solar system, but now with the sun, which indeed is a black hole. Now, you know, the Kepler's laws tell you that the sun dominates the mass in our solar system, and the planets go around on circles or ellipses. And the characteristic, because the mass of the sun dominates, is that the inner planets, Mercury and Venus, are moving faster than the outer planets, Mars and Jupiter and so forth. And the speed of the motion of these planets goes like 1 over the square root of the distance from the star. So if you now, in your imagination, turn that sun into a black hole of the same mass, well, the same motions would occur, and Kepler's laws are still there. So that's the way, in experiments, you might think you could actually detect black holes. You look for the action, the impact of the big mass on the space-time, and therefore the motions of other objects in the vicinity. Now, in the 1960s, for the first time, astronomers discovered objects which are probably such black holes, and they were called quasars. On optical pictures looking like a dim star, but then when looked at with spectra showing that there were lines in these spectra which were redshifted by, in this case of this object 3C273, by 16%, meaning that this object actually is enormous distance away of several billion light years, which at that time was a sensation. And here the theorists, over a 10-year period, then concluded the way to explain this enormous luminosity, 1,000 times the Milky Way with its 100 billions of stars, would be that there are black holes there. Like you saw in this little movie, when you have material fall onto a black hole, before the material disappears behind the event horizon, it can convert its gravitational energy outside of the event horizon into heat and then radiation. And in principle, the theory can predict that you can convert between 7% and almost 40% of the rest mass energy MC squared into radiation. That's about 1,000 times more efficient than how stars produce light, namely through fusion of hydrogen into helium, etc. So that was the discovery of the quasars in the 1960s. and the birth of what we would now call the massive black hole paradigm. But of course, quasars are so far away. How would you test that? How would you test that theory? That's really the question. Now, the answer I've already given you in a way is you try to see whether in the vicinity around such a quasar you have test particles, not planets, but stars, for instance, or gas clouds, whose motions you can determine. And then you see whether that fits with the idea that this is a very massive object in a very, very small volume and has to be a black hole. So this idea was sort of got into thought processes, if you like, in the 1970s, and then it took another 50 years to the current situation, where several pieces of evidence show that indeed there are such black holes beyond any reasonable doubt. One, which I was involved in myself, is using stars to detect the motions of these stars in the vicinity of our own galaxy, our own galaxy being the nearest center of a Milky Way we can go to. And over 40 years, we've been able to basically exclude all other potential alternatives. When I say we, there was a group here at the Max Planck Institute for Extraterrestrial Physics, and before that at the University of California in Berkeley. I'll tell you a little more about it. But also a second group at the University of California, Los Angeles, led by Andrea Ghez, and we independently followed these experiments and observations over the years, getting ever better. And I'll tell you about how important technology plays in this game to come to what looks like a pretty convincing proof. Another big step in this game was the detection of gravitational waves a few years ago, also leading to a Nobel Prize. In this case of the merger of two what we would call stellar black holes. So the black hole in the Galactic Center we would call massive, and that's massive in terms of a few million to, in other cases, billions of solar masses. And stellar black holes, the remnants of massive stars after explosion, have masses of around 10 to 20 solar masses. And if they spiral together in a binary system, well, then in the end, before they get to form a twice as massive single black hole, emits pretty hefty gravitational wave radiation. And that was discovered about 4 years ago and led to a Nobel Prize then. And then finally, the radio astronomers have been able to use what we call intercontinental interferometry. So you take telescopes in far distant places and then interfere the light, which you measure, the radio light, to get very, very sharp images. So in this case, it's in fact telescopes spread over the entire globe to look at a distant massive black hole and see a pattern, which is pretty much what we would expect from a massive black hole with a central dark spot where light is bent and falls into the black hole. So after 100 years after Einstein, on several fronts, we're beginning to have strong evidence that these weird things, black holes, which show up in science fiction movies, really are actual objects which we can see in the universe. But let's now go back to the issue of actually trying to show that such objects might exist. Now, the quasars, which I've explained to you, are very far away, as I mentioned, so far away that any kind of a hope to see motions of stars in quasars is pretty much hopeless, at least at the time. And so Lyndon Bell and Rees, two very famous British astrophysicists, predicted in the 1970s that if black holes, massive black holes, were common, so not only in quasars, but actually in other galaxies, perhaps in all, well, then you could actually go and check out this this hypothesis of massive black holes in nearby galaxies, and in particular, in the nearest of all, the nucleus of our own galaxy. The only problem being that in the galactic center, there is so much dust between us and the center of the Milky Way that you cannot see it in optical light. You have to go to longer wavelengths, infrared wavelengths, radio wavelengths, or shorter wavelengths, X-rays, etc. That was technically not possible in the 1970s, but then slowly became possible with the advent of technology. And in fact, the modern image of the central few light years in infrared light is in front of you. And you basically see enormously bright stars, very massive stars actually, concentrated in the central few light years, a density which is more than 1 million times larger than the stellar density in the solar vicinity. So there would be no night, if you like, if you were on an Earth in this central region. And so it's this region which we are asking whether it might have a black hole in it. In fact, the radio astronomers early on discovered that there was a very compact radio source in this dense star cluster, which I show you here. And in fact, we now know that this radio source, which we call Sagittarius A star, in millimeter waves has a size which is about the same as about 10 centimeters on the moon. So it's a very compact size, only a little bit bigger than what a million solar mass black hole might look like. So given this evidence, one was therefore eager to see whether one could use the motions of gas clouds and stars to verify that there is a large mass here. In fact, in the 1970s, a very famous physicist, Charles Townes, at the University of California, Berkeley, he was the Nobel Laureate for the invention of the maser and the laser, had a research group doing infrared astronomy, and his group built equipment which allowed to look at the Doppler motions of ionized gas and neutral gas around this source Sagittarius A star. The pink are radio emissions from the ionized gas, and the green is neutral gas. In fact, you see these gas clouds are moving very, very fast, as the measurements show, and so fast that one can glean from this evidence that there must be a mass of about 2 to 4 million solar masses in the central few light years. That was the evidence in the 1980s when I joined Townes' group, and we started making that evidence ever firmer. But it wasn't really clear how reliable this was, and surely not whether this must be a black hole. Why? Well, gas clouds can be pushed around with forces other than gravity. For instance, magnetic fields could do that, or winds from stars, and both are present in the galactic center. More importantly, the measurements we had only got to scales of a few light years, which, as I explained, just on the terms of the resolution of the measurements. And that is 1 million times the event horizon size of a million solar mass black hole. So there's lots of other stuff, if you like, which could be here other than a black hole. There could be a cluster of, say, 1 million neutron stars or other faint stars, which would look like a large mass, but does not have to have a black hole. So the evidence we had in the early and mid-1980s was very encouraging for the proof of this black hole paradigm, but it was not convincing, certainly not to others. And so we had to rethink the problem and ask ourselves, how can we do better? And here we needed more spectroscopy. Here we needed better imaging in the infrared with modern semiconductor detectors, which at that time were just being developed. And most importantly, we needed to overcome the effects of the Earth's atmosphere when we are looking at the galactic center. So if you have a distant star send out its waves toward a telescope on Earth, then the atmosphere distorts these. The winds in the atmosphere and refraction together then make the waves unflat and variable, and the images which you get are unsharp and change with time. And the solution for this is to, in fact, measure these distortions and then correct them with what we call nowadays adaptive optics. So you basically have a deformable optical element in the path to correct for the Earth's atmosphere. And then you can indeed get very sharp imagery and achieve the so-called diffraction limit of a big telescope. So you switch on the adaptive optics, and as you see, all of a sudden you actually see very, very, very sharp, including the so-called airy rings. Now, you need to have a fairly bright star to make this correction, and you may not have such bright stars. So another trick we had to pull was to make our stars. These are called laser guide stars. So you basically take sodium D lasers in the lab, put them to the telescope, shoot them up in the sky, and focus them at around 90 kilometers. There's a layer in the upper atmosphere where meteorites, as they come into the atmosphere, get destroyed and rain down as sort of an atomic rain. And there is some sodium in these meteorites, which we are then using as spots to create artificial stars, which then penetrate through the atmosphere and give us a bright enough correction system. So with other words, before we could go to the next steps, including then also bigger telescopes, a lot of technology had to be overcome. And that was the key in this experiment, as it is in most of the natural sciences. And that takes time to actually do it. But then after another 5 or 6 years, we were able to see the first nice motions of stars on the sky near the black hole. So what you see here are images from 3 different years: red for year 1, green year 2, and blue year 3. The green cross is Sagittarius star, and the circle denotes about a light month across. So now we're on fairly much smaller scales than what we had seen before, a light month instead of several light years. And here we can see that these innermost stars clearly show motions of about 100 times the motion of the Earth around the sun. And if at that distance you convert that into a mass, then that comes out to be, again, a few million solar masses. The same mass we had with the gas, but now closer in and very clearly caused by gravity. In fact, you can see Kepler's laws by looking at the fact that the outer stars don't show much of a prism effect. The outer stars are white, while the inner stars have color. And that means, of course, the outer stars are not moving as fast. So that's exactly what you would expect from Kepler's laws. So by the mid-1990s, both groups had pretty much the same result and agreed there was a mass of several million solar masses. Now, further in the gas motions, same mass. So it was already pretty convincing. But must it be a black hole? Well, we're still about 100,000 times the event horizon size of a black hole. So this is not fully convincing. And there were some other even speculative options instead of a black hole. So what would you need to do better? Well, you would need to go further in. You would have to be lucky enough to see a star which comes very, very close to the black hole. And you want to actually see not only motions, but you want to see orbits. The orbits of the stars which you see here typically have periods of several hundred years, or even Max Planck directors won't be able to see that in their careers. But maybe one could get lucky. And in fact, nature gave us stars which we would have not thought possible at the time. which were on very elliptical orbits, or are on very elliptical orbits like this one here, and come very, very close to the black hole. So here's one of these stars, and you can see that this elliptical orbit has in its focus, that in its center, a Sagittarius star. And when the star came at its closest point, which we call the pericenter point, it came as close as 17 light hours away from the center. 17 light hours is about 4 times the orbital radius of the planet Neptune. So we're talking about planetary scales. And here the star is moving at about 3% the speed of light, about 7,500 kilometers per second. And so when both groups observed this star, and we found again the same thing, which you can see by the fact that the blue points from our measurements and the red points from Andrea's measurements really agree very, very well. We concluded, in fact, that the same few million solar masses now had to be within, about 10,000 or even less, 1,000 times event horizon size. So that's already pretty convincing. Now, I should say that this is really unique. In astronomy, usually, we cannot see motions. Of course, we can see motions in the solar system, the planets around us, that we know. But if you look at the distant objects, even the Galactic Center, although the Galactic Center is only 27,000 light years away from us, we cannot see any motions directly. So seeing these motions of the stars is really a stunning experimental confirmation of the hypothesis that there's a central mass for sure, and likely a black hole. And by about 2015 or so, I think we had pretty much everyone convinced, and these results were recognized as the strongest piece of evidence for such massive black holes, as long as general relativity is correct. Because general relativity was very well tested on small scales in the laboratory, in the solar system, and generally at what we would call weak curvature. But here, we are in a totally different regime, near the event horizon of a massive black hole. That's where curvature of space-time is enormous. And of course, if we would be able to go further, which we can't, then the space-time curvature in the center of a black hole would be infinite. So that's the ultimate way of testing general relativity. Now we knew, and Andrea knew, that the star would come back. We knew it had a period of 16 years. So it would be back in another 16 years after the first peri, and that brought it back to 2018. So we had our work cut out for us, because we wanted to now test general relativity for the first time on a laboratory which is 27,000 light years away. Quite a challenge. Now, how to do this? Well, so far we've been using one of these 4 big telescopes of the European Southern Observatory, ESO, in the Atacama Desert in Chile, which is the best site for optical astronomy because nothing grows there. It rarely rains, and the skies are really wonderfully clear and also sharp imagery. So we've used that rightmost of these 4 telescopes, but there are the other 3. And so since I grew up in radio astronomy, I knew that one option to improve the resolution, of course, of these optical telescopes is to combine their light, just like the radio astronomers do. But that's very difficult in the optical because the wavelengths are so short, and also the coherence time of because of the motions of the Earth's atmosphere is only about a millisecond. So you have tremendous technical challenges. But we felt, well, let's try it. And in fact, we formed an international team, a European team, led by one of my senior scientists, Frank Eisenhower, and built an instrument we call gravity, which combines the light of all these 4 giant telescopes and generates essentially a telescope which has 130 meters in diameter. That's the way it's done. Basically, you have individual telescopes. The light hits these individual telescopes, but then underneath, in a tunnel, you bring the light together, and there you interfere it, and you generate a telescope, which is effectively the separation of the telescope. So this improves the resolution and the measurement accuracy by some factor of 20 over what we had before, which was already very good, and allows us to make measurements on the scale of the event horizon. So that really was a major big step forward. So this instrument, gravity, we then brought to Paranal Mountain just before the star S2 was coming back in 2018. So what can gravity do? Well, it can resolve a Eurocent on the moon. A Eurocent on the moon, that's about 10 microarc seconds. That's about the event horizon size of a few million solar mass black hole. And indeed, if you look at these four panels, you can see the instrumental progress in resolution over the years. When we started in the upper left, we were looking with monad-sized telescopes and without adaptive optics, and we could see the biggest and brightest stars, but we certainly couldn't see any details. Adaptive optics and 8-meter telescopes gave us what is then on the right side, which is basically a magnification of the inner part of the upper left image. Now you can see the sharp imagery. You can see also in the center there, that's Sagittarius star. So Sagittarius star itself, the black hole itself, is also radiating, and there are many stars surrounding it. Now with the interferometry, we can now zoom into the little square in the center of this adaptive optics image and blow that up. And in fact, for measurements this year, all of a sudden see there's not only Sagittarius star and not only another star, there's actually a whole set of stars which are all orbiting on solar system scales around the black hole. And when you then make measurements at different times, in 3 different months this year, you can see the motions in color in the lower left inset. And you can see that, in fact, the motions of these stars is enormous, thereby giving us a unique opportunity to test general relativity. So that's how we did it. We started with these beautiful orbits of many stars over many years. Then basically with gravity, we could zoom into the central regions of these orbits and observe those stars which are coming very close to Sagittarius star and move very, very fast. There we can see the motions with high precision and from day to day, not from month to month, and with great precision. So we can measure to 50 times better than what we could do before. And that then gives us the opportunity to test general relativity. One of the effects of general relativity, which is predicted, is the effect on the photons of the gravitational field, as I explained to you earlier. And that results in the so-called gravitational redshift. As the photons climb out of the potential of the black hole and come towards us, there is a tiny little redshift which is generated. So once you subtract the Newtonian motion, then there is a tiny little redshift. The star moves at an orbital speed of about 5, 6, 7,000 kilometers per second, but there is an additional physical effect due to this gravitational redshift, which is about 200 kilometers per second. And you can see in the upper diagram there, the Newtonian orbit is the gray horizontal line. The prediction of general relativity is the red line, and our measurements are these various circles with cyan color. You can clearly see they are not in agreement with Newton, but indeed in perfect agreement with general relativity. Another prediction of general relativity is that all orbiting stars are not anymore on ellipses, but on precessing ellipses. So the Newton's theory basically says that if you have a dominating sun, well, then the shape of the ellipse will stay the same in space, but not so for general relativity. There, the ellipse stays constant in shape, but not in orientation. It starts to basically precess. And the precession for the Galactic Center black hole on this star S2 is about 12 arc minutes per orbit. And in fact, in the right diagram, again, the gray line is what Newton predicts, while the red line in the bottom right diagram is what general relativity predicts. And as you see, at large distances where the red data points were taken, that is true, but then near Perry, all of a sudden, the cyan data points make a kink, as predicted by general relativity, just by the right amount. And so also in this test, it's clear that general relativity is confirmed near such a weird object as a black hole. And finally, we can actually look at the very central region near Sagittarius star itself and look at very hot gas, which emits infrared radiation or radio radiation. Measure the size of the radio source, which is consistent with that of a black hole. And from time to time, see like a little thunderstorm, flares of infrared radiation. And when we observe these flares, we can see that basically the centroid of the location of the flare orbits in about 50 minutes on scales of about 10 times the event horizon size and about 30% the speed of light, just what you would expect from general relativity, but now on the scale very, very close to the event horizon. So it's clear with these data sets going ever further in, measuring ever more precisely, that the Galactic Center indeed has passed all the tests. The one thing which we haven't done yet is to show that there is a spin of the black hole and measure its size, but all of that might be still possible with stars further in. So in these 40 years, we've come from a scale of a few light years and checked to ever smaller scale and showed that the mass was always the same. In a way, a boring result, you could say, but that proved that in fact, all of the mass is, or most of the mass is confined to a few times the event horizon size of a million solar mass black hole. So that makes the proof, I would say, almost incontrovertible. And we only, as I said, we have to show that if we can measure the spin, that this also fulfills general relativity. It's interesting astrophysically that in fact, there is very little outside of the black hole other than the black hole itself. Of course, there's these stars, but they make up only about 0.1% of the mass within the orbits of the stars. But there's nothing much else. Many people had speculated, for instance, that there might be dark matter around the black hole. We don't see any evidence for such dark matter. Or there might be a second black hole, a second massive or intermediate mass black hole. We don't see any evidence for that either. So this gives us very, very important information also about, so to speak, the astrophysical content of this problem. So let me say at the end a little bit more about the cosmic evolution of these massive black holes. What are they good for? You know, why has nature, so to speak, seen to realize them? We could have not, made black holes. Well, we can look back in time by looking further out because the speed of light is finite. So when we look with our big telescopes to very large distances, we can look 10, 12 billions of years back, almost to the Big Bang at 13.7 billion years ago. And when we look at these distant galaxies, we can look at the galaxies as they were 10, 11 billion years ago. And what we find is that many galaxies, in fact, all galaxies we can measure masses in, like for instance, the nearby Andromeda galaxies, have massive black holes. The massive black hole masses, or I should say more conservatively, the concentrated masses in the nuclear regions is in proportional to the mass of the galaxies, as if there is sort of a coupling, a symbiotic coupling of the growth of the galaxy over cosmic time and of the massive black hole it hosts. The biggest galaxies also have the biggest black holes. And the biggest black holes we have found nowadays are almost 10 to the 10 solar masses, 10 billion solar masses. And when we look back in time, we can see that the cosmic rate of buildup of the galaxy through star formation, which is here in blue, and the density of activity of accretion onto supermassive black holes, which is shown by the quasar density here in red, in fact match each other pretty well as you go from the current time on the right side back in time. So about 10 billion years ago, the universe was most active in forming stars. Our own Milky Way forms about 2 suns per year now, and it did then about 100 suns per year. And accompanied by this larger star formation rate was also a larger effective activity of these black holes. So how come? Well, this has to do with the fact how galaxies formed. Initially, if we know, in the Big Bang, there were very few fluctuations which survived after the Big Bang, and the universe, on average, expanded from there on out. But then in small locations were there fluctuations which survived, and they led then to the formation of what we would call dark matter halos, within which, again, galaxies formed, within which, again, black holes formed. And this all was sort of a big dance of gas being transported from the larger scales into the smaller scales through the effects of gravity again. And black holes, on the other hand, being a correction factor, because if you have quasars form, then they spew out so much energy and radiation that they stop the growth of galaxies and turn them into so-called elliptical galaxies. So we understand that the role of these massive black holes is actually very important for the effective cycle of cycling gas into galaxies and then growing them, and then in the end stopping their growth to a system which then basically stays steady. So are we done? Well, we have come an enormous step forward in understanding these black holes, that they exist, that they really are like predicted in general relativity. We would like to basically show that the so-called no-hair theorem applies, which is that there's only 2 things you need to know about a black hole, namely the mass and the spin. And that we might be able to test in 20 years from now, when space agencies, especially ESA and NASA, hope to have a gravitational wave detector in space, which can see the in-spiral of a stellar black hole into a massive black hole. That's probably when I won't be active anymore, or maybe I won't be here anymore, but the story goes on, and it has been an enormously exciting period to test general relativity, to discover these black holes and begin to understand how they formed and evolved. Thank you very much.
Reinhard, thank you for that absolutely wonderful presentation. I mean, you did such a great job of clearly defining the history of the inquiry and the changes along the way, how the new technologies, allowed us to really test the ideas of relativity, et cetera. So I am sure our audience has learned an enormous amount about black holes. I learned a lot about black holes listening to you. That was absolutely fantastic. So the one thing that I always find challenging is appreciating the size of the universe, the numbers of galaxies. And if I'm hearing you correctly, now each of these galaxies has a supermassive black hole associated with it. At least that would be the idea. And I also thought I heard you talk about other types of black holes. So like stellar black holes and so on and so forth. So I walk away feeling like this is something I really didn't know, that there are a huge number of black holes that
Yes.
occupy our universe.
Yes, indeed. Well, my allegory to this is a bit like biology. Astronomy is a bit like biology in that sense. I compare what we're doing, a bit like a walk in a forest which we've never been to. And so we discover as we walk into the forest all these wonderful things. And this is awesome. You see different types of trees and different shapes of flowers and different colors of flowers. And this is just fantastic to explore the phenomenological richness of the universe, just like what you people are doing in biology. But then, of course, comes the point, and here we are going from the sort of exploration to the understanding to physics, if you like, that we begin to see that the blue flowers are always on the left side of the trail. Why the heck? Who ordered that? Who ordered that? And so, of course, there will be first a discussion with your friend who's been walking with you and say, nah, I don't see that. And then so you have to first make, precise measurements of the number of statistics of blue flowers on left side versus right. But after a while, you have agreed, okay, they are all on the left side. Heck, how did that happen? And so that's sort of the wonderful thing, that you go from this exploration to then the testing. And then, of course, in the end, somebody comes on the right side, that's Einstein, and tells you, well, I have an idea how this came about. This has something to do with the rain. Yeah, and so then you test that theory. So that's why I find astronomy, in fact, also biology, so interesting. I mean, I have to confess to you that if I were starting again, I actually wouldn't go into astronomy anymore. I would go into neuroscience, as my daughters, in fact, have done.
I love it. I love it. Well, I guess what I almost had the opposite thought. When I was listening to you and I was seeing, all of the changes that have happened, and relatively recently. Oh my God! I mean, this is a field that has really taken off.
Yes, it has.
In terms of really providing strong evidence, for theories that I'm sure Einstein, he would be blown away seeing how his thoughts, have materialized. Now let me ask, are there any examples that you've seen that challenge general relativity? I mean, that don't quite fit with the picture that we would expect?
I know that's a very good question, and I think the answer is a resounding yes, yes, and yes. Why do I say that three times? Well, the first time is because this is now more of a sort of a theoretical yes, because of the prediction of Einstein's theory that all the mass is in a central mass singularity. And singularity, again, let me define what I mean by singularity. I mean that all of the mass, independent of whether this is a 10 solar mass stellar black hole or a 10 to the 10 solar mass supermassive black hole, all of that mass is in a point, okay, with less than the so-called Planck length in size, with basically infinite density. And every reasonable quantum physicist would say that can't be. That must be wrong. And what's the blunder? Well, there's no blunder. It's just that, as in other theories, which we've had the pleasure in physics to explore, there are limits to which a certain theory is correct, and it has to be amended to a quantum theory of gravity, which would then, if you like, soften this central singularity from a point into another shape and another size. And of course, as physicists, while we almost certain that this has to be the case, we don't know how to get there. And the practical problem is we can't do an experiment. That's really, that's really bad news. So the atomic and nuclear physicists found ways to check out whether the proton or the electron were point particles, which were predicted by electrodynamic theory, right, initially, and found out that they aren't. But they could make theory experiments. Well, I tell you, even if I'm courageous enough to put myself into a rocket of Bezos and fly to the Galactic Center and make it there, sorry, I can't report to you what I found. Okay, so that's a conundrum which is very awkward, very awkward. Number two is the second, so to speak, time when these black holes, in a way, or infinite curvature spacetimes occur in astronomy, is the Big Bang. And there too, there is something where most people, most physicists would say, that can't be, that there is a state of infinite density. It's not infinite size, infinitely small size, but infinite density at some finite time. And then if somebody asks, and what was before, you can't answer. Now that's no good. Okay, and we don't have an answer. And the third thing, the third yes, is the experimental detection of the so-called accelerated expansion of the universe. It's clear, we know, everything we've learned in physics has sort of these simple principles like energy conservation. Energy conservation. So if you have a finite amount of energy, you have a finite universe, and you put bang into it, explodes clearly enough, you would expect it to expand to a maximum size when the kinetic energy is all used up in terms of the potential energy, and then, falls back together. But no, the frigging thing expands even faster now than it did, a billion years ago. How come that? That can't be. And again, okay, that's a verified fact now. A Nobel Prize went for that. We call it dark energy, but we don't understand what it is. And there, again, something is fishy here. And that's interesting. If something is fishy in physics, that means it's going to get very interesting pretty soon, because fishy means maybe if you have better technology or a better theory, you might find new physics, okay? So there's the prescription for next generation of physicists to go to understand all these things.
And I would say what you just said there about fishing applies to neuroscience just as well. And I was going to ask you, along the way, was there a time where you saw something and you just kind of shook your head, whoa, what is that? That doesn't make sense. And and I think every scientist has that moment where, oh, that must be some technical problem and so on and so forth. But can you think of a time?
Yeah, well, I could give you numerous examples in this Galactic Center story, which you just heard about, where every theorist, including Nobel-winning theorists, would have told you that this is impossible. The most striking one is the existence of these stars on planetary scales, happily orbiting on elliptical orbits. Why? Well, we have a fairly well worked out equilibrium theory how gravity works in a dense star cluster. And basically what happens is, since gravity is a long-range force, you're transferring energy between these different stars over long periods of time, because you don't typically come very close, okay? Now, of course, in a dense star cluster, you can, if it's dense enough, have a collision here and there. So there's an exception, but that's very, very rare. Most of the time, the stars sort of fly by each other and exchange energy. So you can calculate that if you have a certain initial state of your star cluster, how long it'll take that it takes another state. So in fact, when you put a big black hole into the center, you can ask, what is the final configuration? The final configuration is sort of a concentration of stars around the big black hole, with some stars actually falling in, but very rarely, and a very slow contraction over typically a timescale of 10 billion years. These stars which you've seen orbiting on planetary scales, they are only 10 to 20 million years old. They can't have wandered in there. They never would have done so in their lifetime. So who got them in there? Well, somebody who aimed pretty well. You have to take your gun and shoot it right into what we call a lost cohort orbit. And so we don't understand that quite yet, how that happens, but it's there. So if we come back to the issue of how you do research, this is where working in the Max Planck environment, one of the many times when I was so glad, because I just could write to the Director General of ESO and say, we would like to propose an experiment to do the following thing, and we've got the money for it, but you just have to give us a little bit of telescope time. And he would say, well, maybe. Had we had to ask for money, the peer review committee would have told us, these stars you need to see these motions don't exist. They don't have time to get in there. So forget it. Just forget it. Yeah. So I could tell you several such stories in the Galactic Center, and it's just absolutely fantastic. And in fact, this year again, the star which was our star and Andreas' star S2, which was our sort of main champion for all these years. Well, okay, it went through Perry in 2018 again, and now it's halfway back out. It'll come back in 2036 when I'm underground, but I won't see it anymore. So should we give up? Well, we didn't, and sure enough, this year 4 stars are going through Perry.
Yes. Just
because we now have the technology to look on these scales, which we didn't before. See, this is the best. You combine what is predictive improvement in your experiment with the chances and the luck, actually, that nature gives you sometimes.
Yeah, nature leads the way here to new insights, new discoveries. Last question, I can imagine some in our audience would be wondering, are there any direct effects of the massive black hole in the center of our galaxy on Earth? I mean, are there ways in which this may be exaggeration, but that, our lives, our daily lives are impacted by things that might be happening in the black hole?
No, the answer is no. And I would say we can have a fairly good, bet on the stock market that it won't in the future. Okay. Why do I say that? Well, I mean, basically, gravity doesn't do the trick because the mass of the black hole is, as I said, about 4 million solar masses. The mass of the Milky Way is, 100 billion solar masses, and so by the time you're out at the radius of the Earth, we are at sort of 2/3 out of the size of the Milky Way. The mass of the inner galaxy in terms of stars and the rest of it is totally dominating the mass of the black hole. So it's not, gravity can't do it. What about radiation? Yep, that can happen. The radiation and particle emissions, jets, plasma streams. And in fact, that's how these quasars probably affect their galaxies. We see that directly. I mean, there's other experiments we are doing. We're looking at these galaxies 10 billion years ago, and we look exactly at the effects of the quasars onto these galaxies and see how they're blowing out material in a hurry so fast that they undoubtedly will stop the star formation in a fairly short period of time. So that is clear, that can happen. Exactly how the mechanism goes, we're not sure yet, but that it happens, we are sure in many ways, including the fact that we see the remnants of these galaxies which were stopped from growing as these elliptical galaxies in our local environment. So yes, it could have, but only at that time. Nowadays, the universe, as it's expanding and then even in an accelerated fashion, ever less gas is making it into the Milky Way. Okay, as I explained, the growth rate and therefore the gas accretion rate into the Milky Way was 50 to 100 times larger than as it is now, and it's going to go down ever more. It's going to get ever boring, more boring in the universe, and nothing is going to grow much, including the black holes, actually. And so in the future, there is no problem. In the past, we were lucky that we were not in a galaxy which unfortunately went through a quasar state. So in that, we were lucky to be born, to be hosted in a at that time relatively small disk galaxy, and not in a big galaxy. Then it would have gotten us.
Well, I think we should probably wrap it up. And Reinhard, once again, thank you so much for your wonderful presentation. And I'd like to invite you to visit Jupiter. Jupiter, Florida. Okay.
Okay. Yes.
Sometime in the future, we would love to see you here and talk more about all of these exciting discoveries. Thanks again, Reinhard.
Okay, then. Good to see you.
Thanks for watching Curiosity Meets Discovery, research talks from inside the Max Planck Society. Visit mpfi.org to sign up for updates. Follow us on social media at MPF Neuro. Curiosity Meets Discovery was produced by the Max Planck Florida Institute for Neuroscience.